This meeting is being live streamed. Got it. It started getting.
Okay, it seems like it automatically started, so you can just go ahead.
Okay, good. So thanks everyone for joining. This is our next PNS Ramulator meeting. In today's meeting, I'm invited to guest talk. I'm Geraldo, a PhD student here in Safari with Onur, and I work mostly on processing memory architectures. And today I'm going to present one of the processing memory works that we did called SimDRAM. This work was published in last year's ASPLO, and it's titled SimDRAM, a framework for bit serial CMD processing using DRAM. And feel free to stop to ask any question on YouTube or over Zoom. I will do my best to answer the questions. So, okay, so first I'm going to start with a high-level summary of the talk. So, our primary motivation in this work is the crescent interest on processing using memory architectures, which can effectively perform bulk bitwise operation. However, we observe that such architectures are not yet widely applicable, since they only support a limited and rigid set of operations, lacks the flexibility to support new operations, and often requires significant change to the DRAM subarray in order to enable complex operations. Currently, our goal in this work is to design a processing using DRAM framework that can efficiently implement complex in-DRAM operations at low cost, while providing the flexibility to support new desired operations with minimal modifications to the DRAM architecture. To this end, we introduced SimDRAM, which is an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for to implement arbitrary operations in DRAM as required, using a massively parallel in-DRAM SIMD substrate. Our evaluation shows that SimDRAM can provide 88 times and 5.8 times the throughput and 257 times and 31 times the energy efficiency of a baseline CPU and a high-end CPU, respectively, for 16 in-DRAM operations. Besides that, we evaluate SimDRAM using seven real-world applications, and we see that SimDRAM can provide 21 times and 2.1 times the performance of a CPU implementation and GPU implementation for such workflows, respectively. So here is the outline for this talk. First, I'm going to briefly talk about the problems of processing using DRAM architectures. Then I'm going to give some background on DRAM and also processing the baseline processing using DRAM architecture that we will consider this work. Then I'm going to talk about SimDRAM, briefly talk about our system integration, or evaluation, and finally to conclude. So I'll start discussing processing using memory. So the increasing prevalence and the growing size of many modern applications have led to the high energy and latency costs for computation in traditional computer architectures. Prior works have shown that the cost of data movement between main memory and the CPU across the bandwidth limited and power hungry memory channels in such is much higher than that of computation, and can consume more than 60% of the total system energy in modern systems, making data movement a major bottleneck in today's systems. To mitigate such costs, the processing memory or PIM paradigm moves computation closer to where the data resides, reducing and in some cases eliminating the need to move data between memory and the processor. Processing using memory is one of the promising approaches of processing memory, which makes use of the operational principles of the memory cells themselves to perform computation by enabling interactions between the cells. Since processing using memory operates directly in the memory arrays, it benefits from the large internal bandwidth and parallelism available inside the memory arrays. A common approach for processing using memory architectures is to make use of bulk bitwise computation, as many widely used data-intensive applications such as databases, neural networks, and graphic analytics heavily rely on a broad set of simple logic operations such as AND, OR, and XOR, and more complex operations such as addition and multiplication. I will now give a brief background on how DRAM operates and how its operating principles can be used to build processing using DRAM architectures. A DRAM model is composed of many DRAM chips. Each DRAM chip is composed of several DRAM banks, Each bank has many subarrays, which are a 2D array of DRAM cells. The 2D array of DRAM cells are horizontally connected via a word line and vertically connected via a bit line. The bit lines are connected to an array of simplifiers called row buffer. A DRAM cell is composed of a storage capacitor, which holds the data stored in DRAM as charge, and a access transistor, which enables and disables the charge flow from the storage capacitor to the bit line. The DRAM cells operate using three main commands: activate, read and write, and precharge. To read a charge level stored in the storage capacitor, the memory controller first issues activate command. Prior to receiving the activate command, the bit line is held under a reference voltage, usually half of VDD. First, once the DRAM array receives the activate command, the word line of the target row is asserted, which connects all cells along the rows to their respective bit lines. Second, the storage capacitor shares charge with its corresponding bit lines. And third, the simplifier is enabled, and fourth, the resulting bitline voltage shifts is sensed and amplified by the bitline simplifier. Once the simplifier finishes amplification, the row buffer will contain the value originally stored in the cells along the asserted word line. Also, the charge is stored in the capacitor, and the capacitor is fully restored. At the end of the activate operation, the DRAM array is ready to receive read and write requests from the memory controller. The memory controller then issues read and write comments to columns within the activated row. To prepare the DRAM array for further access to DRAM rows, the memory controller issues a precharge command. It works as follows. First, the capacitor is disconnected from the bit line by disabling the word line. Second, the bit line voltage is restored to its quintessential state. Now the DRAM array is ready for the next access. And third, the simplifier is disabled. Now, let's see how we can use the internal DRAM operation principles to perform in-DRAM computations. First, we will see how we can perform in-DRAM row copy. Let's assume we want to copy the values stored in source row A to destination row B. The two rows share the same bit line. Row clone enables copying a source row A to a destination row B in the same subarray by issuing two consecutive activate commands to these rows, followed by a precharge command. This command sequence is called activate precharge. It works as follows. First, we issue activate commands to the source row A, which will copy the contents of the source row A into the row buffer. We then issue activate commands to the destination row B, which connects the cells in the destination row B to the bit lines. Because the simplifiers have already sensed and amplified the source data by the time row B is activated, the data in each cell of row B is overwritten by the data stored in the row buffer, thus copying the data in source row A to destination row B. Finally, we wish to activate commands to prepare the DRAM array for the next access. We can also follow similar principles to execute majority function in DRAM. A true input majority outputs 1 if and only if at least two of the inputs are equals to 1. Let's assume we want to compute the majority function between three rows, row A, row B, and row C. All two rows share the same bit line. The authors of EMT shows that simultaneously activating three DRAM rows via a DRAM operation called triple row activations can be used to perform big bitwise Boolean operation on the values contained within the cells of the three rows. Let's see how it works. First, when activating three rows, three cells connect to each bit line, share charge simultaneously, and contributes to the perturbation of the bit line. Upon sensing the perturbation, the simplifier amplifies the bitline voltage to VDD or 0 if at least two of the capacitors of the DRAM cells are charged or discharged, respectively. As such, a triple activation results in a Boolean majority operation among the three DRAM cells on each bitline. In this example, the majority of row A, B, and C will be equals to VDD. The result of the majority operation is then overwritten to all three DRAM cells. To end the operation, the memory controller needs to issue a precharge comments to prepare the DRAM array to future access. MBIT uses the row activation command sequence to implement Boolean and NOR operations by simply set one of the inputs, for example, C, to 1 or 0. The AND operation is computed by setting C to 0, since the majority of A, B, and 0 is equals to N or A and B. The OR operation is computed by setting C to 1, since the majority of A, B, and 1 is equivalent to A or B. In order to perform processing using DRAM, MBIT makes use of a subarray organization that incorporates additional functionalities to perform logic primitives. MBIT splits the DRAM rows into three main groups. First, designates 16 row address as compute rows, which can execute triple row activations. We call this group the bitwise group. Second, Mbed pre-initialize 2 rows with all ones and all 0 values. These rows are used as control rows for AND and OR logic operations. We call this group the control group. Third, Mbed uses the remaining DRAM rows as regular data rows, which store users' data. We call this group the data group. Mbed requires minimal modification to the DRAM array, namely a regular row decoder that can activate rows in the data group and control group, and also a small row decoder that can address the bitwise group. This special row decoder can simultaneously activate 3 DRAM rows using a single address, which perform a majority operation between the 3 activated rows. Mbed imposes less than 1% of area overhead in existing DRAM systems. Many prior works follow up by Mbed by exploring DRAM designs as well as other memory technologies that are capable of performing computation using memory. However, 3 major shortcomings prevent these proposals from becoming widely applicable. First, they support only basic operations, for example, Boolean operations or addition, and fall short on efficiently support more complex operations, as for example, multiplication or division, which limits their applicability. Second, they support only a limited and specific set of operations, lack the flexibility to support new operations that cater to a wide variety of applications that can potentially benefit from processing using DRAM. And some prior works propose processing using DRAM designs that support more complex operation, but however, such works require significant changes to the DRAM subarray, which make them quite costly. All of these problems highlight the need for a framework that can aid the general adoption of processing using DRAM by efficiently implementing complex operation while providing the flexibility to support new desired operations. Therefore, our goal in this work is to design a process using memory framework that can efficiently implement complex operations, provide the flexibility to support new desired operations, and minimally change the DRAM architecture. I will now describe our proposed processing using memory framework called SimDRAM. We introduced SimDRAM, an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex in-DRAM operations and providing the ability to implement arbitrary operations as required. SimDRAM achieves this using an in-DRAM massively parallel SIMD substrate that require minimal change to the DRAM architecture. I will now describe the DRAM substrate that SimDRAM uses for in-DRAM operations. We built SimDRAM framework around a DRAM substrate that enables 2 key techniques. First, a vertical data layout in DRAM. Prior works have shown that employing a vertical layout for in-DRAM operations eliminates the need for adding extra logic in DRAM to implement bit shifting operation, which is essential for many complex operations. Employing a vertical data layout provides SimDRAM with 2 key benefits. First, we can do implicitly shift operations, and second, a massive parallelism, wherein each DRAM column operates as an independent SIMD lane. The second key technique used in SimDRAM substrate is the majority-based computation. As opposed of using Boolean basic logic operations such as AND or NOT to implement in-DRAM computations, SimDRAM uses the logically complete set of majority and NOT operations to implement in-DRAM computation. This provides this enables SimDRAM to achieve higher performance and higher throughput and lower energy consumption compared to using basic logic operations for in-DRAM computation. Next, I will describe how a framework works. SimDRAM is an end-to-end framework that provides the user with the ability to implement an arbitrary operation in DRAM. The framework is composed of 3 main steps, which are illustrated. Going to be illustrated in the following picture. It takes as input and or not a representation of a desired operation. Then, in step 1 of the framework, we build the efficiently majority not representation of a given design operation from its and or not based implementation. Specifically, this step takes as input a design operation and uses logic optimization to minimize the number of logic primitives and therefore the computational latency required to perform the operation. The second step allocates DRAM rows to operation inputs and outputs and generates the required sequence of DRAM comments to execute the desired operation. This step output is a microprogram which is an optimized sequence of DRAM comments that is stored in main memory and will be used to execute the operation during the execution time. The microprogram is stored in main memory and will be used to execute the operation. And a new SimDRAM instruction called BBOP is created as an interface to the microprogram and then added to the CPU ISA. The third step, during the third step, we SimDRAM take the microprogram to perform the operation transparently from the user. To do so, SimDRAM uses a control unit in the memory controller that can transparently issue the sequence of DRAM comments as dictated by the microprogram. Once the microprogram is complete, the result of the operation is held in DRAM. Now, let's look into the first step of the SimDRAM framework in more details. As empty showed, it's quite trivial to convert a Boolean equation from to its equivalent majority equation. As each two-input AND is implemented using a three-input majority primitive, where one of the inputs is tied to 0. And OR primitive is implemented using a three-input majority primitive, where one of these inputs is tied to logic 1. Accordingly, the first part of the transformation process in step 1 of the SimDRAM framework simply replace AND and OR primitive with majority primitives. However, naively converting AND and OR primitives with majority primitives we use the implementation of the operation that correctly replicates the functionality of the initial AND and OR not-based implementation, but is likely inefficient. To address this issue, the second part of the transformation process takes the inefficient majority not-based implementation and uses a grid algorithm to apply a series of transformations that consolidates multiple majority primitives into smaller numbers of majority primitives with identical functionality. This yields an optimized majority not-based implementation that requires fewer logic primitives to perform the same operation that the unoptimized implementation performs. For example, here in this picture, the generated majority not-based circuit for a carry propagation logic in a full adder require only one majority logic primitive instead of 4 majority primitives. Therefore, step 1 generates optimized majority not implementation of the desired operation. Let's now take a more detailed look in step 2 of the SimDRAM framework. Each SimDRAM operation is stored as a microprogram, which is a series of microarchitecture operations such as activation and precharge that SimDRAM uses to execute SimDRAM operations in DRAM. Accordingly, the goal of the second step is to take optimized majority not-based implementation as generated in step 1 and convert it into a microprogram that executes the desired SimDRAM operation. To this end, the second step of the framework performs 2 key tasks on the optimized majority-based implementation of the operation. First, allocating DRAM rows to operands, which assigns each input operand of each majority operation to a DRAM row, and second, generating the microprogram. Now let's take a look at the first task of step 2. The goal of task 1 is to allocate DRAM rows to input operands of each majority primitives in the majority not-based implementation of the operation. When allocating DRAM rows to operands, SimDRAM takes into account 2 extra constraints that are specifically of processing using DRAM. First, the number of compute rows which are going to be used for computation in the subarray are quite limited. Second, performance majority in DRAM has a destructive behavior. In other words, the triple row activation overrides the original value of the 3 input rows with the output of the majority function. Based on these 2 issues, we present a new allocation algorithm inspired by the linear scan register allocation algorithm. Our allocation algorithm takes as input the majority not implementation of the operation generated in step 1 and starts by assigning the inputs of each majority logic primitive to available compute rows, one at a time. Since the number of compute rows are limited, the 3 here in this example, this step of the algorithm assigns only as many input as the compute rows as the number of compute rows that are not allocated to any operand yet. Next, performing the triple row activation in the compute rows computes the majority of A, B, and the carry in this example, which in fact computes also the carry out value. As a result of the destruction behavior of the triple row activation in DRAM, the carry out is stored in all 3 input rows at the end of the triple row activation. Our allocation algorithm takes advantage of this behavior and reuses the rows for all row operations allocation in the next round of tuple row activations. In this case, the value stored in these rows is an input for the next majority function. Now, let's take a look in the test 2 of step 2 of our SimDRAM framework. Test 2 works in three parts. The first part generates an initial microprogram. This part first copies the three operands from the data rows to DRAM rows allocated from task 1 using row copy operations, which consists of 2 activations followed up by a precharge operation. Once all the inputs of the majority are copied to the allocated rows, a tuple row activation is issued to execute the majority logic. Finally, another row copy is issued to copy the output of the majority storing the compute rows back to the destination data rows. The result sequence of DRAM comments represents an initial microprogram. In the second step, we optimize the initial microprogram by leveraging the instruction of our process using DRAM substrate, including the ability to coalesce multiple row copies operations into a single one and merging a majority and row copy operation into a single operation. With these two optimizations, test 2 of step 2 generates an optimized microprogram that requires fewer DRAM operations to execute the same desired operations. We invite you to check our paper for more details about the two optimizations discussed here. Once all potential operations are coalesced, the framework now has an optimized microprogram that computes the desired operation for an operand size of 1 bit. The final part of test 2 generalizes this 1-bit version of the operation into an n-bit version by repeating the DRAM comments into the optimized microprogram for any times. The final outcome is an optimized microprogram that can execute bit serial computation over a flexible precision in DRAM. The final microprogram is then stored in a reserved region of DRAM for future use. Also, a new SimDRAM instruction called bbop is created and added to the CPU ISA. The SimDRAM instructions are used later by the programmer to perform the added SimDRAM operation. Now, let's take a more detailed look at step 3, the final step of the SimDRAM framework. SimDRAM uses a control unit in the memory controller that handles the execution of the microprogram during the runtime, transparently from the programmer. To perform a SimDRAM operation, the programmer uses a bbop instruction. Upon receiving this instruction, the control unit loads the microprogram corresponding to the bbop from the main memory and performs the requested SimDRAM operation by issuing the sequence of DRAM comments stored in the microprogram of the SimDRAM operation. At the end of the microprogram execution, the outcome of the SimDRAM operation is stored in the main memory. Now, we discuss the integration of SimDRAM in the system. We employ several techniques to efficiently integrate SimDRAM in the system, including how to efficiently transpose data, how to define a program interface for SimDRAM, how to handle page fault, address translation, coherence, and interrupts, how to handle the limit size of a subarray in DRAM, the security of applications of processing using DRAM, and the limitations of our framework. The first technique is regarding the efficiently transposing of the data layout in DRAM that enables SimDRAM to store the data required for in-DRAM computation in a vertical data layout. While SimDRAM operates on vertically layout data, the other system components, including CPU, expect data to be laid out in a horizontal data format, making it challenging to store data to share data between SimDRAM and CPU instructions. To address this issue, SimDRAM uses a specialized hardware unit placed between the last level cache and the memory controller, called the transposition unit, to transform the data layout from horizontal to vertical and vice versa. The transposition unit tracks SimDRAM objects and ensures that its corresponding data is in a vertical layout and ready for SimDRAM computation, where the data is in DRAM, and in a horizontal layout where whenever the data is in the cache and is ready for computation in the processor. Our evaluation shows that the transposition unit imposes very low overheads on the throughput of SimDRAM operations, while imposing very low area overheads. We employ several other techniques to efficiently integrate SimDRAM in the system, as also how designing programming interface for programming SimDRAM. So we design 4 new SimDRAM instructions to enable the programmer to interface with SimDRAM operations. Those instructions fall into the following categories. So we have initialization instructions, which are used to demarcate which regions of memory are going to be touched by SimDRAM operations. We have one input operations, which are, for example, Boolean reduction of operations. We have two input operations, which are, for example, addition or multiplication arithmetic operations. We have predication operation, which enables the computation to execute if and else operations. So here I have an example on how you can transform a C code to a SimDRAM code. So in this C code is a simple code that executes a vector addition or subtraction operation, depending on some condition. So in the and then in the other box we have the equivalent code using SimDRAM operations. I highlight some of the important transformations that are required for the SimDRAM code next. So here, the first step of implementing SimDRAM code is to use the BBOP transpose initialization operation to tell the system which arrays or memory regions are going to be touched by SimDRAM operation and thus need to be transposed by your transposition unit. Second, we open the loop and now we can issue the equivalent addition, subtraction, and greater operation for the predication execution. And finally, we issue the predication execution to figure out if you want to execute addition or subtraction operation. In the end, we have a much smaller version, much simpler implementation of the code that can execute a SimDRAM capable instructions. We invite you to read our paper for more details about the transposition unit and the rest of the SimDRAM system integration techniques. I will now present the results of SimDRAM. We implement SimDRAM using the Gen 5 simulator. We compare SimDRAM against three baselines: a multi-core CPU, a high-end GPU, and also Mbed, a state-of-the-art in-DRAM computing mechanism. We evaluate three different configurations of SimDRAM. One bank configuration where a single DRAM bank is extended to enable SimDRAM computation. This enables SimDRAM to execute operations over 64,000 SIMD lanes. We also evaluate SimDRAM with 4 in-DRAM computation-enabled banks and 16 in-DRAM computation-enabled banks. To demonstrate its generability, we evaluate SimDRAM using 16 complex in-DRAM operations. Those ranging for simple operations like addition and subtraction to more complex operations like division and multiplications. And also we use 7 commonly used, we implement SimDRAM operations in 7 commonly real-world applications from varying domains, including neural networks and databases. So first, we compare the throughput across all 16 SimDRAM operations normalized to the 3 baselines. Here, the x-axis shows each one of the 3 baselines we evaluate, and the y-axis shows the average normalized throughput in giga operations per second. We make the following observations. First, SimDRAM with a single bank provides 5.5 times the throughput of the baseline CPU, and this value increases to 22 times the throughput of the baseline CPU using 4 DRAM banks, and to 88 times of the throughput of the CPU using 16 banks. Second, SimDRAM with a single bank is not enough to outperform the throughput of the GPU. However, with 4 DRAM banks, SimDRAM provides 1.5 times the throughput of the GPU, which scales to 5.8 times when you use 16 DRAM banks. Third, compared to Mbed, SimDRAM 1 bank provides 1 times the Mbed throughput, while SimDRAM with 4 banks provides 7.9 times, and with 16 banks, SimDRAM provides 31.6 times the throughput of Mbed. We conclude that SimDRAM can significantly outperform all state-of-the-art baselines for a wide range of operations. Second, we compare the energy efficiency across all 16 SimDRAM operations normalized to 3 baseline systems. Here, the x-axis shows each one of the 3 baselines we evaluate, and the y-axis shows the average normalized energy efficiency in throughput per watt. We make the following observations. SimDRAM provides 257 times the energy efficiency of the CPU baselines, 31 times the energy efficiency of the high-end GPU, and 2.6 times the energy efficiency of Mbed. We conclude that SimDRAM is more energy efficient than all state-of-the-art baselines. Third, we compare the speedup across all the 7 real-world applications. First, SimDRAM with a single bank provides three times the speedup compared to the baseline CPU, which scales to 8.7 times using 4 DRAM banks and 21 times using all 16 SimDRAM capable banks. Second, SimDRAM with a single bank and with 4 banks is not enough to outperform the GPU. However, SimDRAM using 16 banks provides an average speedup of 21 times compared to the GPU. Third, SimDRAM with a single bank provides 2.5 the speedup compared to Mbed, which scales to 7.3 times using 4 DRAM banks and 17.5 times using 16 SimDRAM capable banks. We conclude that SimDRAM can efficiently and effectively accelerate many commonly used real-world applications. Please read our paper for more evaluations on the reliability of SimDRAM operations, the data movement overhead and data transposition overhead of SimDRAM, the area overhead of the SimDRAM, the overall SimDRAM proposal, and a comparison to a previous proposed in-cache computing mechanism. All of this in your paper. Now, let me conclude giving a summary of the SimDRAM work. So in this work, we introduce SimDRAM, end-to-end processing using DRAM framework that provides the program interface, the ISA, and the hardware support for efficiently compute complex operations and providing the ability to implement arbitrary operations using DRAM. Using all of this using a massive parallel in DRAM single substrate. We have extensively evaluated SimDRAM, and we see that SimDRAM provides 88 times and 5.8 times the throughput and 257 times and 31 times the energy efficiency of a baseline CPU and a high-end GPU, respectively, for 16 in-DRAM operations. Also, we evaluate SimDRAM using real-world applications, and we see that SimDRAM can provide 21 times and 2.1 times the performance of the CPU and a GPU of over 7 real-world applications. We conclude that SimDRAM is a promising processing using memory framework that can easily the adoption of processing using DRAM architectures and can improve the performance and energy efficiency of processing using DRAM architectures. So thank you so much for listening. And again, I invite you to check our paper through this QR code here in the screen. So thank you so much. I'm going to check if we have any question from Zoom or for the YouTube link. So we don't have any question from YouTube. Is there any question from Zoom? Let me check. Sharing. I guess we don't have any question from Zoom also. So thanks everyone for listening to this talk, and feel free to send me any questions or any comments via email. So thank you so much.